Hi, and welcome to this ICASS presentation on a divide and conquer approach for sparse recovery. My name is Nitin Jonathan Myers, and I'm an assistant professor here at the Dell Center for Systems and Control. Today, I'm pleased to be talking about this piece of research by Aaron Bevelander, who was my former master's student, together with Kim Batselier. So, we started looking at this problem of sparse recovery in extremely high dimensional space. Particularly, we were looking at reconstructing signals with close to a million or hundreds of millions of entries. And it turns out that to recover such extremely high dimensional signals, standard CS algorithms suffer from two major issues. The first is that they result in extremely high computational complexity, and the second is that they occupy a significant memory footprint. Today, we'll see how these two issues are addressed using the framework of block compressed sensing, and I'll talk about our contributions towards block compressed sensing. Now, before we get started with block compressed sensing, it's important to introduce the notion of compressed sensing at a high level. So in CS, we are interested in recovering a sparse signal X from its linearly compressed version. Let's say X is the unknown sparse signal. It has few non-zero entries, and many of the entries in X are zeros, which are indicated by the white boxes. So X gets compressed to a measurement vector Y, and the goal of compressed sensing algorithms is to reconstruct X from Y. Now, from basic linear algebra, you know that this is a hard problem when m is much smaller than n. Particularly, you may end up with infinitely many candidates for x that lead to the same y, right? However, under the assumption that x is sparse and a is well constructed, you can uniquely recover x. And that's exactly the key idea of compressed sensing, which has been applied to a whole bunch of applications. Now, the motivation for this work stems from the fact that as our sensing technologies get advanced, the dimension of the sparse signal increases significantly. And due to such high dimensional signals, you end up with a big problem wherein compressed sensing algorithms suffer from memory and computational issues. So let me give you some insight into the computational bottleneck. So let's say you use a standard compressed sensing algorithm such as the greedy orthogonal matching pursuit. What's important to note here is that for O of 1 sparse signals, the complexity of the OMP is dominated by matrix vector multiplications over here. And the complexity of these operations scales as O of mn, where m is the number of measurements and n is the dimension of the signal. Imagine what would happen if n is several hundreds of millions and m is several tens of thousands. The complexity would just blow up, right? And sometimes it may not be even possible to run these algorithms on a standard desktop computer. The way to get around this problem is using the framework of block compressed sensing, BCS. The idea in BCS is to break the high dimensional sparse signal into different blocks. In this work, we consider blocks of equal size, and one such block is shown by x1 over here. So in BCS, you can rewrite the measurement model y equals ax into the form shown over here, where the assumption is that the CS matrix A has a block diagonal structure. That is, its energy is concentrated about the diagonal, and all these entries marked in dark here are 0. Now, when you have such a structure, you can break y equals ax into different subproblems, where the first subproblem solves for x1, the first block in x, from y1 equals a1 x1. The second problem solves for x2 from just y2 equals a2 x2 and so on, right? When you are able to break y equals ax into beta different subproblems of this form, naturally the complexity of solving each subproblem is lower, right? It goes down by a factor of beta square. And the complexity of BCS is O of mn by beta square with the OMP if we are able to solve all these beta subproblems in parallel. If you're not able to do that, due to memory issues, we could solve for these sub-problems in sequence, and even then we get a complexity reduction by a factor of beta, right? So BCS has these nice advantages in terms of low complexity and low memory footprint. Then what's the problem with BCS? Well, today we are going to see that partitioning the sparse recovery problem results in worse reconstruction performance. Alright, and to alleviate the performance loss due to partitioning, we are going to develop an algorithm that makes use of information learned from one block into the reconstruction of a different block. So first, let's get started in analyzing the impact of partitioning on sparse recovery. Before we study this impact, it's important to introduce the notion of mutual coherence, which is defined as the maximum absolute inner product between distinct columns in A. For greedy sparse recovery algorithms such as the OMP, a low mutual coherence results in better sparse recovery. So how low can mu be? Well, it's known in the literature that mu can be as low as a Welch bound shown here, right? Note that this Welch bound depends only on the dimensions of the CS matrix A. When M is large, the Welch bound gets smaller, right? Now, in this work, we are particularly interested in studying such a bound when the CS matrix A has a block structure. For such block structured matrices, we showed in our paper that using the definition here, mu can be expressed as the maximum of the individual mu's for each of these submatrices that are colored. Okay, and by simplifying this further, we were able to arrive at this result shown here, where mu of the block CS matrix is lower bounded by this quantity shown in the middle, right? Note that in BCS, beta is larger than 1, right? In standard CS, you can interpret that as a special case of block CS where beta is 1, correct? And by examining this function, you can see that the bond that we have for block CS is higher than the coherence bond for standard CS for the same dimensions, right? And this is expected because in block CS, we have an additional constraint on A that all these entries have to be 0, right? When you force these entries in A to 0, you are left with fewer degrees of freedom to play with the other entries in A, and that naturally increases the coherence bond, right? So we plugged in the coherence bond that we derived into the reconstruction error bound with the OMP, and what you see is the plot on the right, which says, well, as you increase the partitioning in the problem, right, as you increase the number of blocks, the reconstruction error gets worse, right? So how do we solve this problem? Well, we are going to make use of information learned in one block in reconstructing the other block, right? And before we explain how this information is propagated in reconstructing different blocks, it's important to know how a signal needs to be partitioned into blocks. Right? So to this end, we consider the clustered sparse signals which occur in our near field channel estimation problem, right? So this is an example of such a signal. As you see, the non-zero entries occur in a cluster, right? We looked at two ways to partition this clustered sparse signal. The first is contiguous partitioning strategy, which groups all the coefficients over here into one block, then the coefficients over here into the next block, and so on, right? Now, if we were to go with block compressed sensing using such a partitioning strategy, then we see that in the first iteration, when we solve for the first block, we just get zeros, and that doesn't provide any useful information about the non-zero entries in the remaining spots, right? With the other comb-like partitioning strategy, however, you do end up with useful information when you solve for one block, right? So let's say this is the comb-like structure highlighted by the pink boxes here. And after I solve for the sparse signal supported on the pink boxes, let's say I estimate the non-zero component in the green box, right? Now, information about this green box, together with the knowledge that the signal has clustered sparse structure, gives us prior information on the support of the neighbors here, right? And this prior information can be learned from the data set itself. That is, given that a particular coefficient is non-zero, what is the probability that its neighbor is non-zero? This is something that you can learn in a data set, right? So in this work, we make use of knowledge about the support correlation kernel together with the block compress sensing framework. What we do is we just solve for one block, right? And after solving for one block, we derive the probability that these coefficients over here are non-zero, right? And that is derived using the information learned from the data set together with the reconstruction, right? And we make use of these probabilities while we solve for the second block, right? And that's when you get that. And then you solve for one more block and the final block, right? So a summary of our algorithm is shown over here. And as you can see, we solve for one block, make use of the reconstruction here together with the support correlation kernel learned from the data set to determine the prior that a particular entry over here is non-zero, right? Now we use that prior to solve for the next block, all right? So this procedure is carried out until we hit all the beta blocks in our problem, all right? Now let's take a look at the results for near field channel estimation. As you can see over here, standard BCS for beta equals 1 is the same as standard compress sensing, right? Because if beta is 1, that means that I don't partition the problem at all, right? Now partitioning to 16 subproblems worsens the performance as you see here, right? Now with our proposed approach, which exploits support correlation across different blocks, you end up with lower NMSE when compared to standard BCS that solves for all the 16 blocks independently, all right? So in this work, we showed that by exploiting support correlation across different blocks, you can enhance sparse recovery when compared to standard block compress sensing. Okay. Now this enhancement, however, comes at a small price, right? As you see here, the computation time with our method is higher than standard block compress sensing. And the reason is because our method requires updating the support correlation kernel as we move forward in the BCS pipeline, right? So in summary, today I showed that partitioning a compress sensing problem can lead to poor reconstruction performance. Okay. Now partitioning is favorable because it has advantages in terms of memory and computational complexity. However, performance is worse. That's something to keep in mind. And we also showed that by propagating information from one reconstructed block into the other, you can enhance performance with BCS. Okay. So thank you and see you at ICASSP.